Electromotive force. This is actually a misnomer. We think of a force as a push or a pull, but in actuality, this electromotive force is not a force, but really a potential difference. It does create the conditions where we're going to move charge. Of course, there's going to be a force on the charge carriers, but in actuality, electromotive force, EMF, is really measured in volts. It's a potential difference. It tells you that for a particular system, how many joules of energy we're going to get for a unit of charge. So sources of EMF are basically devices that convert one type of energy into electrical energy. This electrical energy is going to enter the system through this EMF, through this potential. Now, in terms of sources of EMF, probably the most important ones that we talk about are the galvanic voltaic cells. These are essentially what we know to be batteries. Hydrogen fuel cells, of course, also convert chemical energy into electric energy. Electromagnetic induction, we talk about later on with Faraday's law of induction, where we can see how a generator can create an EMF through a changing magnetic field. Of course, we've got to do work on the system, so it's really the mechanical work put into the system that creates the conditions for converting mechanical energy into electrical energy. Thermal energy, thermocouples or thermopiles are examples where heat flows across a device. This is actually used on the Mars rover, where they use radioactive decay to heat up part of this radioisotope generator. It goes across these thermocouple or thermopiles and converts some of the thermal energy. It's not very efficient, but some of the thermal energy is converted to electricity. Very reliable, not very efficient, very reliable because there's no moving parts, and all you need is a heat source. Radioactive decay from this plutonium there generates a heat source for decades, and you can get electricity without many modes of failure. Finally, another example, certainly not the last example that we can come up with, but the last example that we have listed here are photovoltaic cells. This is where we take light, the electromagnetic energy, and we convert it into a potential. So all of these cases really give us the opportunity to take one form of energy, we want to store the energy, and convert it into electrical energy for use. The galvanic cell, or sometimes known as voltaic cell, named after the discoverers, basically combines two types of chemical reactions. An oxidation reaction. With an oxidation reaction, for instance, zinc going into solution, it loses 2 electrons. Oxidation reactions lose electrons, and in the process, energy is given off. Reduction reactions, we have an ion in solution gaining electrons, and that, of course, corresponds to an energy change. It's really the oxidation reaction which provides positive energy. We put energy into the reduction reaction, so it's a difference between those two reactions that determines how much energy we get out of this. Now in this case, we have one of the simplest type of so-called galvanic or voltaic cells, where zinc is in a solution containing zinc ions, copper is in a solution containing copper ions, and as the zinc goes into solution, the copper comes out. As a result, we are giving off positive ions, so we're building up negative electrons here. The electrons will then, of course, generate an electric potential. Here we're losing electrons, so we also create a potential over here. And it's that potential difference which allows us to do work across here, for instance, to light up a bulb. So again, with these cells, we have these half reactions that take place, ions entering solution, ions leaving solution, and that's the principle behind these galvanic or voltaic cells. The term battery actually means a series of these devices. We use it now generally to mean any galvanic or voltaic cell, but its original meaning was to take many of these and put them in series to get a larger voltage. Now here are some different electrode potentials which are associated with the reactions that take place. And this really determines what voltage we get from a battery, what the potential difference is going to be. In this case, you have a positive electrode voltage. Down here you have negative electrode voltages. So all of these electrode voltages are really in reference to hydrogen losing an electron and going into solution. That is given a zero potential. So what we will typically do is make one electrode which is going to draw ions out of solution. Usually it's a fairly non-reactive metal like copper, gold, or silver. These are, of course, copper is the cheapest. We'll have a positive electrode voltage compared to hydrogen. And then we have a metal that tends to easily go into solution. And here we have lead, tin, nickel, cadmium, iron, zinc. Down here, sodium, potassium, and lithium have been metals that are so reactive that they're difficult or have been difficult to incorporate into a battery. We'll see that with lithium-ion batteries, we've played a few tricks to actually take advantage of lithium's very, very large negative electrode reaction. So again, putting different electrodes together, it's the electrode that really determines what our voltage is. Here, for instance, is a zinc carbon battery. We've combined zinc and carbon as the two electrodes. We have basically a paste in between the two where the ions are going to basically reside. Here are the general formats that we have for these type of batteries. The largest, of course, are called D, then we have C, AA, AAA, you've definitely seen these. The 9-volt battery is actually 6 of these 1.5 volt batteries put together. This AAA battery right here is actually one of these units. If you put 6 of them in this package, a 2x3 grouping of them, and then put them all in series, you get the 9 volts. Here's our lead acid battery. With a battery, the electrode potential doesn't necessarily tell you how much energy they can store. With these batteries, the bigger the battery, generally the more energy that they're going to have within them. A D cell is going to last longer than a C cell, which is going to last longer than a AA, lasting longer than a AAA. The amount of material that you have in here really determines how many ions you have, and at that given electrode potential, you take voltage, which is joules per coulomb. More ions, more coulombs, more energy. Okay? So lead acid batteries, these are really large batteries which we use to provide the energy to start an internal combustion engine. And what we can see here is that we have these plates within it, and some of the plates are lead, some of the plates are lead oxide, and it's the lead going into solution and coming out of solution which generates this large electric potential. Now, looking at this, it's actually, the 12-volt battery is actually 6 2-volt batteries. Lead acid batteries actually have a potential difference of 2 volts. But when we put them in series with 6 of them, we get 12 volts. Now again, the larger the battery, generally, the more energy that it's going to store. The also important thing about this is larger batteries have smaller internal resistance, which means that they're going to be able to deliver more power when we need that power. Here is the lithium-ion batteries that we find in a Tesla. Tesla, of course, has been making these electric cars and really pushing the rest of the auto industry to rethink the use of internal combustion engines. What's interesting is we're now storing the energy, instead of in a fuel tank, in these modules which sit at the bottom of the car. This is actually advantageous because a lot of the weight of the car actually comes from these batteries. And each individual battery itself is then inserted into these modules. These modules are then wired together. at a fairly high voltage, in fact. It's actually, each battery itself is about 3.7 volts. When you hook them all into parallel in series to create these large modules, we actually get, in some cases, a few hundred or even over 1,000 volts. So currently, these electric cars actually can store 74 kilowatt hours. Remember, a kilowatt hour is 3.6 million joules. So that's a total of 2.7 times 10 to the 8 joules, or 270 million joules of energy. And again, for the Model 3, which came out recently, that's 4,416 lithium-ion batteries. They're grouped in 6 cells per brick, and then the bricks are grouped into modules. The modules are then wired together to produce the energy. The whole battery itself weighs about half a ton, or I should say the whole battery unit weighs half a ton, so that's significantly more than the weight of a fuel tank in a car. But again, these are much more efficient energy-wise. So let's take a look at some of the advantages and the limitations of batteries. Again, battery, that's our source of energy. That is our EMF, electromotive force, that is going to provide chemical energy, which becomes electrical energy, and power whatever we hook up to it. Now here I have it in series with a resistor. The resistor generally converts electrical energy into heat. Now, you can hook anything up to this. You can hook an LED up to it. LEDs convert electrical energy into light. You can hook a motor up to it. The motor will convert electrical energy into mechanical energy. But resistors are fairly simple. We're going to use those as an example because simply they dissipate the electrical energy in the system. So we get energy from the battery. We dissipate it through some resistor. It's important to note that as the battery is operating, it has its own internal resistance. What this means is that yes, as current flows through the resistor, we're going to lose the energy in the form of heat through the resistor, but the battery itself will actually get warm. If you've ever noticed when you're charging or discharging a battery, it gets warm. That's because with internal resistance, we know the power that is converted into heat, the power that's converted into heat is equal to I squared R. The higher the resistance of the battery, the more energy it's going to dissipate as we put current into it to charge it. In fact, this is one of the dangers that we have with recharging batteries. Electric cars take a long time to recharge. So one of the problems that they have with using these superchargers, which dump a lot of current into the battery very, very quickly, is the internal resistance heats the battery up. And if you don't dissipate this thermal energy, the battery can actually shorten its life and become damaged. So again, when we're hooking any electrical load up to a battery, we have to be cognizant of the fact that there's going to be internal resistance. We're going to lose energy simply by drawing current from that battery as it's converted into heat. So when we look at the terminal voltage, what we get out of the battery, we don't always get that full rated amount. So let's say that this is a car battery right here rated at 12 volts. If I draw a little bit of current over here, power loss is equal to I squared R. If I don't draw a lot of current, then my voltage is not going to drop very much. However, if I draw a significant amount of current from this, okay, I lose more power here. I actually get a voltage drop here, okay? So the total 12 volts that I expect becomes less. You can see this sometimes when you turn on a car. The lights actually get somewhat dim because the voltage coming out of that battery will actually decrease. So, internal resistance of the battery means that my terminal voltage is not necessarily equal to the EMF. I will lose some voltage on a battery as I draw more and more current. Again, if it's a really small battery, it is going to have a much higher internal resistance, and therefore the voltage is going to drop very quickly as I draw more and more current. Larger batteries can sustain a higher terminal voltage for the same current because of their lower internal resistance. So again, internal resistance, our expectation is for very, very small batteries, they have a high internal resistance. They're not really designed to give you large current loads, okay? And that's fortunate that most electronic devices are designed to use transistors that have small amounts of losses. But as we get to larger and larger objects, let's say a starter motor on a car or an electric motor, again, you can't use small batteries to power them. They just can't deliver the power due to their internal resistance and their own energy limits. So again, when we're looking at the internal resistance and EMF, the total power from the energy stored in the battery goes by the current times the electromotive force, whatever that battery is rated at. Some of the energy is lost through whatever resistive load we have on there. Again, going back to this diagram right here, we want the power to get to where we're sending it. We want the power to be given to our resistive load, whatever is on there. However, again, it's not insignificant that the power that we lose in the battery, and this power becomes almost exclusively heat. Okay? Now, chemical reactions increase with temperature. So again, if you discharge a battery too quickly, you can heat it up, you can damage it. If you charge a battery too quickly, again, that power is dissipated. This works both ways. We don't want that thermal power to overheat the battery. Let's take a look at 3 different batteries and look at the terminal voltage with each. Again, let's go back right here. Terminal voltage is equal to the EMF of the battery, what it's rated for, minus that loss due to the internal resistance. So the bigger R is, the faster the power is going to drop, the faster the voltage is going to drop. So these very small pill batteries are designed to power, small devices, maybe hearing aids, maybe a small calculator. They're not really designed to provide very much energy. So as I draw more and more current from them, the potential across the positive and negative electrodes drops more and more until finally, if I try to pull too much current from them, my voltage is going to drop to 0. Larger batteries, medium internal resistance, they can generate more current, okay, right at the same voltage, but again, eventually come to a limit. Large car batteries, a tremendous amount of material within them, lots of ions, low resistivity. The lower internal resistance means that you're going to be able to draw much more current from them. So, a 12-volt battery, you can start a car with that because of the current demands this thing can handle it. Okay? Can't take a small battery and start a car with it. There's just not enough energy stored within the battery, and the higher internal resistance, you're never going to get near the currents that you need. Again, there are many different types of chemistry that we use to create these galvanic and voltaic cells. Zinc carbon, of course, is inexpensive. These are the typical batteries that you can buy without much cost. There's a zinc chloride version of this which uses a chloride paste, where you see some of these D cells, AA and AAA batteries. They'll call them heavy duty. They'll use that type of chemistry. Similar are the alkaline zinc manganese dioxide. So they use an alloy of zinc to raise the amount of energy that's stored within there. But again, these are all 1.5 volt batteries based on the chemistry of the zinc and the carbon that are in them. Okay? Just the way that they set them up, they can get different energy densities. We'll talk more about the lithium batteries, the lithium ion batteries. We don't make mercury oxide batteries anymore. Those were some of the high button ones I'm sorry, the small button batteries, zinc air. We've gone from mercury oxide to mainly zinc air for those types. Silver oxide, obviously it's very expensive, also used in the button cells. Nickel cadmium was used for rechargeables for quite a long time. There is a concern, as with lead, that cadmium, being a heavy metal, is toxic and a real problem for the environment. The nickel metal hydride batteries were popular to some extent, but again, lithium-ion batteries are becoming sort of the norm for energy storage. They have a very good number of cycles that we can charge them, depending on their chemistry. They are very expensive, but as the number is increasing, they're going down in price. And this is an interesting graph. If you want to look at battery performance, this shows the energy, ignore watt hours. Then we're looking at power and we're multiplying it by time, we're getting energy. And down here we have watt hours per liter, watt hours per kilogram. So for the heaviness of the battery, the further up on the y-axis we go, the lighter that this battery is going to be for storing a certain amount of energy. If we're looking down here, this is looking at size. So obviously energy per unit size, again you see that the lithium-ion batteries really do quite well when we compare them to like the old lead-acid car batteries.